All right, so here we go. We're going to attempt to look at question number 33, which is a little bit more crazy than the others. So we're going to apply the ratio test, and that's going to look just like this. The limit as n goes to infinity of 6 to the n plus 1 over n plus 2 to the n plus 1. Now, this is an exponential function. It's not polynomial anymore, so that looks like it might be a little trouble. Reciprocate the nth term, and then we're going to try to simplify as much as possible. Sixes are going to be easy. We're going to be left with the 6 up top. Here's where we're going to run into trouble here. We have n plus 1 to the n. We have n plus 2 to the n plus 1. The first thing I'm going to try to do is get it so that we do have a common base. It's easier to work with it that way. So, actually, not a common base, a common exponent. So the n plus 2 to the n plus 1, I'm going to write as n plus 2 times n plus 2 to the n. So you can see when you multiply those together, you added the exponents, you would get n plus 2 to the n plus 1. The only reason I did that is now I can look at that exponent part, and it's the only part with an exponent, as one rational expression to the n. So if you apply the limit here, you're going to get 0 times this. Now, if this is a constant number, that's good because we'd have 0 as the limit. But I'm not really quite sure what it is. You might assume it's 0, thinking like the degree of the bottom is bigger than the top, but it's not a rational expression. So we're going to have to try to find this limit, maybe using L'Hopital's rule. So if you remember the little trick for that, we're just going to take the limit as n goes to infinity of n plus 1 to the n plus 2, which is infinity over infinity, to the infinity. We can't have that. It is indeterminate. So we're going to set it equal to y, and to get rid of that exponent, we're going to natural log both sides. So I'll have the limit as n goes to infinity of n times the natural log of n plus 1. So I did that all at once. What I did was I took the natural log of both sides. Because of the continuity of the natural log, you can put it on this side of the limit. So the natural log of the limit is the same thing as the limit of the natural log. So since I have the natural log of this, I brought down the power of n, and now I can see if L'Hopital's rule can apply easier. It usually does if you don't have an exponent. This would be infinity times 0, which is still indeterminate. But if we creatively write this as a fraction, usually that will work. So that's exactly what I'm going to do. I'm going to creatively write it as a fraction. Instead of n on top, we can make this 1 over n on the bottom, because you multiply reciprocals when you divide fractions. So this is the same thing. So we have the natural log of 1, which is 0, over 1 over n, which is 0, or 0 over 0. So we're good to go. I think I misspoke up here when I was looking at this. When I applied this limit, I had infinity times 0, and it's because it was the natural log of 1. So I don't know if I said that, but that's infinity times 0, which is indeterminate. So now I change it to this. We have the natural log of 1, which is 0, over 1 divided by infinity, which is 0. Now we have infinity over infinity. So we can apply L'Hopital's rule to this. Take the derivative of the top. And the top, I'm going to make it a little bit easier on myself. I'm going to think of the top as the natural log of n plus 1 minus the natural log of n plus 2. Use properties. So the derivative of the top is just 1 over n plus 1 minus 1 over n plus 2. And the derivative of the bottom is negative 1 over n squared. So now when you plug in infinity, I'm getting 0 minus 0, which is 0 over 0. Oh, no help. So let's combine this. Let's see. 1 over n, I might as well do it. We have n plus, we're going to get a common denominator. So we're going to have n plus 2 up here minus n plus 1 up here. So n plus 2 minus n minus 1. So it's just going to be 1 up top. Well, that works out nicely. And then multiply by the reciprocal of the bottom, so it's a negative n squared over 1. And it's still the limit as n goes to infinity. Now when we take the limit as n goes to infinity, we get negative 1. So it's strange, but that's okay. Exponentiate both sides. So we have y, e to the natural log of y is y, equals e to the negative 1, or just 1 over e. So we got our answer, but now I forgot what we were doing, so I have to go back up top. All we were trying to do was figure out what the limit of this part of our expression was, because we knew that 6 over n plus 2 was going to be 0. So if we could find out that this limit was some constant, we'd be in business. And guess what we just did? We found out that that limit, that limit was, I don't know why I'm writing this over again, but I'm doing it anyhow. That limit was 1 over e. So when we plug in the limits, we get 0 times 1 over e, which is 0, which is less than 1, which means we have, drum roll, absolute convergence. So there you go. That was number 30. I even forget what number it was, 33. So I hope you enjoyed that.